I'm Brad Hodges. I'm a senior principal with SMRT. Architects and engineers, we're in Andover, Mass., Portland, Maine, just outside of Albany, New York. I'm a licensed engineer by trade, fire protection engineer, and for about the past 27 years I've been working almost exclusively in controlled environments, predominantly on the microelectronics and semiconductor fab side, which is kind of morphed into defense, intelligence, and aerospace. Some of the clients that I'm dealing with on a regular basis would be BAE Systems, the Raytheon Corporation, Draper Labs, GE Healthcare. A lot of exciting stuff, but I'm kind of bringing the electronics side to the table today.
Hi, I'm Jeff Talc. I'm the Life Science Practice Leader at SMRT. I have about over 30 years experience in science and technology, life sciences. Been doing it around the country, around the world. Very fortunate to do work in Korea and Saudi, not Saudi, but Dubai. Currently we're working with people like Sanofi, Pasteur, L'Oreal, LabCorp, amongst a few others. So anyway, I guess we'll start.
And to just summarize, what we're hoping to touch on are the different types of clean rooms, and we're really looking to compare and contrast the electronic side of house and the life sciences. That's really our main objective. There are many kinds, but we've boiled it down to those two kind of broader categories. A lot of commonalities, and you'll see that. And there are some differences, subtle at times and more than subtle at other times. Trying to touch on the regulations and the standards. What are the things that, what are the agencies and the documents out there that we design to? We're going to speak to some trends, what we're seeing new in the industry, as well as some of the new tools and techniques we have for defining and help shaping these spaces. And certainly we're going to touch on energy. These spaces are extremely energy intensive. There are some things you can do about that, and there are other things that at times you have to live with, but we'll get into that as well. So just briefly, what is a clean room? High level. Why do we need a clean room? Why do we need a controlled environment? We're trying to control particulate and contaminants is what it comes down to. And what that does is it provides for safety for the people working in the space, but it also provides safety for the product. People can mess up a product. People and contaminants can decrease yield and make being productive very difficult. Safety, 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 and certainty of outcome. Again, increased yield. In a nutshell, this is a very generic representation of what a clean room is. It's a space that's generally positively pressurized compared to surrounding areas. It can be negative, and we'll get into that a little bit. Air is pushed through the ceiling through HEPA filtration, and then it's either returned through a raised floor if you have one available, or it's returned through low sidewall, back up and around and around. That's how you deal with your particulate control. You also have makeup air that's pushed into the space for a few different reasons, to pressurize the space and also to provide makeup and compensate for exhaust you're going to pull out of the room. Well, that takes a lot of energy because you're preconditioning the air. So whatever you're pushing into the room, you're going to overcool to wring out the moisture, you're going to reheat, you're going to get in within the tolerances that you need and push the air into the space. Again, all of that nicely conditioned air, much of it will go out the exhaust stack, unfortunately. And then the other component you have is sensible cooling. So you've dealt with the environmental conditions. What about the heat gain from people in the room? What about heat given off by processes and equipment that's located in the room? We'd call that sensible cooling. So you're going to have some means, and there are a variety of approaches that you could take to providing that sensible cooling. So again, really high level, that's your clean room.
Yeah, and just one interesting thing about that diagram is that it illustrates the concept of a box in a box, which is also applicable not only to electronics fabrication, but also life safety and high containment as well. So what's cleaner? An operating room or a clean room? Anybody hazard to guess? You're wrong, it's a clean room. Yeah, operating rooms operate at a level of about ISO 7. We'll get into that, and Brad will explain that very well. Clean rooms obviously will go up to, or down to ISO 5, etc. Some of the typical applications of clean rooms, obviously within the life sciences, and we'll also showcase electronics and related industries. Pharma, biotech, compounding, high containment, I mentioned. Medical device is kind of a straddler. It goes within life sciences because it's regulated by the FDA, but the manufacturing mostly resembles a clean room that you would see in microelectronics.
And that could be single-use disposable items. It could be any number of things that are used that would go into a body. Kind of the next pivot from that would be into medical equipment. We did a substantial facility for GE Healthcare outside of Albany, and that was a medical equipment manufacturing space that was they were making the brains of the digital mammography machines as we were making the pivot a few years back from paper records to digital records. Medical equipment feels and looks like semiconductor, but again, it's right on that line. And then again, traditional semiconductor, kind of slightly lower tech electrical assembly. And then aerospace is really a growth market that we're seeing with things in the atmosphere, things outside of the atmosphere, the privatization of the space marketplace, popularity of more smaller satellites as opposed to fewer and more vulnerable larger satellites. So aerospace is semiconductor-like, and it's a lot of work that stays stateside, which is interesting as compared to much of the semiconductor market.
Yeah, just some graphic examples in the pharmaceutical business. This is a QA/QC lab for a major vaccine manufacturer. Brad's going to get into a little bit about gowning. So this is pretty much the level of gowning kind of matches the cleanliness level and the activities that'll happen within those spaces. So, but this gives you a general idea of the kinds of finishes and fixtures and laboratory casework that you would see, and utilities that you would see in a life sciences pharmaceutical laboratory. Biotechnology, this is a university-based genomics laboratory. A lot of movable casework. Everything is plug and play up in the ceiling. Again, this is a kind of an institutional look because it is a university. Readily clean, but actually warm fronts, things like that. Some high containment, not only dealing with microorganisms, but also some radiological tagging and things like that. So again, when I mentioned the box in the box, that's kind of the premise for a high containment. And high containment basically is negatively pressured as opposed to a manufacturing facility that would be positive. So that's going to have a lot of impact on the way you set up mechanical systems, and that will be evident later.
Food and beverage, as you can imagine, is generally a sanitary environment, but there are small areas, and we'll talk a little more later about mini environments. Bottling line, we do quite a bit of bottling plants for Nestle Waters, and where you're doing the filling and you're doing the capping of the product, that's going to be done in a controlled environment, in a positively pressurized, contained area. But that doesn't mean you need to make the whole factory or the whole warehouse necessarily a clean space. They're expensive. You don't want to over-apply them. You want to use them where they're necessary, but you don't want to over-apply them for that reason, for the cost reason. Again, semiconductor, really at the heart of what many of us think of when we think of a traditional clean room. And next one, electrical assembly, which a little further on down the line, back end of line type of processes after the manufacturing is winding down and you're doing packaging and assembling. Again, aerospace. SpaceX, whether it's spacecraft or satellites, there's lots of application. It's not just about NASA anymore, and a lot of the defense giants and not so giants are getting more and more into things that aren't just in our atmosphere, and they're playing a role in providing components and systems and sub-assemblies that would be part of a larger program. And if you think of like the F-35 Joint Strike Fighter program, I think it's Lockheed Martin, every defense contractor has a piece of the pie, whether it's a guidance system, whether it's weapons, whether it's radar. Everybody's doing something different, and they're pulling them together. So a lot of work to go around there.
You had mentioned earlier that you were seeing an increase in aerospace types of companies. Are you talking specifically in New England or further afield?
I think the aerospace business in general growing. I don't know so many more companies when it comes to the defense contractors you're used to seeing. It's just a kind of a ratcheting up of activity that they're having. The new companies we're seeing are like the SpaceXs of the world, where there are players who weren't traditionally in the market, and they're not coming at it from an angle of being an entrenched defense contractor, but they're coming at it fresh, So we're just seeing a lot of spending and activity with BAE, Raytheon, Northrop Grumman, Lockheed Martin, a lot of the traditional companies. It's not just about the in the atmosphere type of products anymore. And that leads to other changes that we'll get into a little bit later on new materials that people are using.
But at the outset of every project, or whether it be a small renovation or a ground-up facility, we need to talk with the owner and kind of identify what their goals are. Obviously, the bottom line is the dollar, and we have to gear our design methodology towards that. So some of the things that owners look for is workflow, space use, people flow. You want to become more efficient. You want to become workmanship needs to be more effective and yield a higher profit when you're dealing with product. The company culture. We want to institute a very good work environment, and that actually leads to more production, things like that. Economics. There's the long and short-term economics as well as the overall cost of ownership. What's it going to cost for the 50 years that I'm going to own this facility? It's this first cost, it's operating costs, it's depreciation, there's a whole lot of things, maintenance, repair, things like that. So,
and is it 5 years, or is it 50 years, or is it 25 years? That'll lead to a lot of the decisions about the type of systems that you're going to be able to apply.
And actually, the way things are done, be it research or production, evolves over time. And it will evolve quicker than the life of the building. So we need to look at future-proofing and flexibility. And what we like to say is don't let the facility get in the way. Don't make the facility formulate what the scientists can or cannot do. The facility needs to be flexible. And obviously, there's utmost safety. A lot of companies that we deal with, safety is number one. And there are 3 factors that lead to a safe environment and an energy sustainable and a cleanliness environment. One's facility design, the second is the equipment that's being utilized, and third are the protocols. And our mission and our task as architects and engineers is to optimize the interaction of those 3 factors to yield a product that's the most cost-effective and safe for our clients. So for instance, you can really be lackadaisical on your protocols, but that might have an impact on the kinds of facilities you'll have, like additional anterooms, additional air handling systems. So by doing that, you might not get the biggest bang for your buck. So again, it's a good synergistic relationship between those 3 factors. And the owner's program will always change, and that's a given. Here's an example of a project I worked on doing lab fit-outs in Tampa. The project was an incubator facility, essentially. And the program had 60% offices, 40% labs. Well, the way it got fit out was exactly the opposite. So you can see that there are a lot of additional things that had to be put onto this building in order to make it work. This was basically a double-loaded corridor facility with a penthouse in the middle, and that kind of led to some impediments in terms of the planning of the floor plates. But the message is things will change. You don't have to do the infrastructure to anticipate all the changes. You need to provide the conduit and the pathways by which the additional products, ductwork, et cetera, can be put through the building. There's another one downtown Atlanta. This building was 10 years old and was completely obsolete. It's a research building. I worked on a chemical vapor deposition laboratory, which was down the hall from BSL-4 cabinet lab. And you can see that there are 24-inch stainless steel ducts running up and down the building to accommodate that because the infrastructure couldn't work and there was no pathways internally to run those critical systems. So what we've been seeing, what we've been looking at is what we're calling this saddlebag approach, where that you take all the utilities and all the maintenance people outside of the laboratory itself. And this is actually the CDC Building 23 in Atlanta. And you can see this is the finished product CUH2A did while I was there. So the laboratories have glazing, which look over glazing from the mechanical service chase. And all the servicing from the laboratories are done outside the laboratories within reach, without a ladder, within that service galley.
What did you call the approach?
Called a saddlebag. A saddlebag or service galley.
So backing up a little, how do you define a clean room? Federal standard 209E has been around forever. It was actually discontinued in 2009, but it's still referred to a lot. When you hear someone talking about a Class 10, Class 100, Class 1000 clean room, that's following the 209E standard. Since it's been discontinued, the ISO 14644 is a standard that ANSI and IEST jointly developed, and that's the ISO 7, ISO 6 class, and we'll compare and contrast the two in a moment. Those really apply across the board, whether you're in life sciences or electronics. The FDA, DEA, USP, and others have other add-ons, and Jeff's going to get into those a little later, to define things as they pertain within the life sciences area itself. We also find sometimes we're doing work for the government, and the UFC, the Unified Facility Criteria, the codes and standards that the federal government has don't really address these things that well. So you end up having to add on quite a bit and pull in some of these other standards to fill in the gaps that exist in the UFC standards. So again, the ISO class, 209E class, what does this all mean? If we take a Class 100 clean room, or ISO 5, another name, what it means is you're going to have no more than 100 particles that are 0.5 micron in size and larger in a cubic foot of air. So in any cubic foot of air, you're not going to have any more than 100 particles of that size. The air changes per hour, we'll pivot back to that later. This is kind of the older way that we're getting away from, a prescriptive approach, saying that if we run the air through these HEPA filters 400 times an hour, that's going to ensure that we're going to be at a level of Class 100, ISO 5. Just to give you some context, a micron is a millionth of a meter. A human hair is about 75 microns across. So we're talking tiny, tiny. Even as the width of Ebola is less than that, the overall length is such that it's going to get caught in a HEPA filter. A HEPA filter, high efficiency particulate arrestor, is a pleated type of filter. That's what's located at the ceiling level of these clean rooms, with either a central station air handling fan pushing air through it, or individual fans coupled to every filter. And HEPA filters are going to pull out 99.99% of particles, 0.3 microns and larger. So we're talking very small levels, but depending on what you're working on, those particulates at that level can really mess up your operations. So again, as they pertain to electronics, you can imagine that the Class 10, Class 100, the smaller the number, the cleaner. At that level is where the microchip fabrication is happening. I refer to it as a wafer. If you're not familiar with it, a silicon wafer and other material wafers, and a number of computer chips are built on that silicon substrate. Then they're broken apart into individual chips after the fact. So they're routinely referred to as a wafer fab. So those fabrication processes are happening in the cleaner areas. Then you get into the mid-level, Class 1000 and 10,000, ISO 6 and 7. You're getting into the kind of the sub-assemblies, test, assembly, and packaging. Class 100,000 is the dirtiest of the clean areas, and it's generally where your ante-room or initial vestibule would be, your gowning. You're not just going to walk from a room into a clean room. You're going to go through one or a series of ante-rooms. The term white room is no more than a space built to Class 100,000, but you're not certifying it. You're not looking to officially have it be monitored as a clean room, but you're going to build it to that standard.
And then when you get into the life sciences realm, there's the concept of CGMP, or Current Good Manufacturing Practices, which is basically an overlay of the ISO. I list the ISO at rest and the ISO cleanliness in operation as approximations. They're really not correlated one-to-one. But the cleanliness levels, A, B, C, D, controlled, not classified, unclassified, really stems out of the European Union, GMP, Annex 1. And what that is an attempt to standardize nomenclature and standards globally, because a lot of the companies that deal in the pharmaceutical and biotech business are international companies. So we need to standardize that. So A being the most clean, these are for critical aseptic GMP zones. And also another thing I wanted to point out is that ISO typically deals with particulates. The ABCD would also are levels of aseptic or sterile environments, meaning no biologicals. So it's kind of a double-edged sword there. It's particulates and it's microorganisms. So level A is typically a place where the environment will come into contact with the product. It's normally done in a biosafety cabinet or similar facility, whereas the background room would be a B and then C. And as you progress from the locker rooms into the deeper and deeper clean levels, you go through ante-rooms and do different gowning, et cetera, et cetera. So there is a progression. You go from D to C to B, and you don't jump to, for instance. So.
What are the drivers when we look at planning, designing, and constructing a space? Well, again, we've talked about a little bit about how clean is clean. However you classify it, looking at the standards, you're defining what you're doing and how clean the space has to be. Then you're looking at the HVAC implications. What are the temperature and humidity targets and tolerances? You know, what do we need to do to make people comfortable? What do we need to do to make the product happy and the equipment happy? Exhaust air, all of those factors go into the HVAC side of a house. There are the physical constraints. You know, not often do you get to build, not often, often you don't get to build a greenfield clean room, greenfield anything. There are a lot of renovations out there. Do you have the headroom that you need to put the amount of equipment up above the ceiling? What do you have for structural integrity? You know, you get into the class 1000 and class 100 spaces that have a level of HEPA coverage where you have quite a robust ceiling. Sometimes we have to put in a steel substructure underneath the framing of the building to support the ceiling system. Vibration, we get into vibration often where what does your process require and can you achieve that with the existing space that you're in without isolated slabs or anything else. And then there's infrastructure. Aside from the clean envelope itself, what are you doing in the room? You need compressed air, compressed gases, liquid chemicals, liquid cooling water, purified water, there, power, backup power, emergency power, clean power, UPS. There are data, classified, unclassified. There are a whole host of utilities to support whatever pieces of process equipment are going to sit and operate in these rooms. Code really builds off the first one. I guess the one code story I'd talk about, I think we'll get to it a little later, talking about HPMs, but hazardous materials, hazardous production materials are commonplace in these environments, so that's another whole level of attention that you have to pay to the design and the layout of these things. Earlier, Jeff touched on cost of ownership. Again, you might do a building that someone's going to lease from the government for 50 years. You might do something that a startup with not much money is just getting out of the gate with. Completely different animal in terms of the systems that you select. The makeup and exhaust balance is key, touched on that. Accommodating phased occupancy. This one's huge. We often think of what's the overall load, what's my tonnage of cooling I need, how much air do I need to push out of a makeup unit. Well, you're thinking of when the suite is fully built out. What if it's done in 4 phases and you're going to operate at 25% fit out for a year? Can you turn down your air handling equipment in your chiller plant to that low end? That can be the gotcha often more so than the high end. Understanding how something's going to be phased, timeline, and can you hit that low end with your systems and equipment. HPMs, one thing I'd say there is we did a project for a client downtown Cambridge where we were consolidating clean room operations into one suite on an upper floor, and the idea was we were going to take the hazardous gas room that supported that space and also move it. Well, you're limited in how the volume of hazardous gases of all variety of types that you can store, that you can have in use. Every level you go up in a building, it's reduced how much you can store in one certain place. In the end of the job, we ended up leaving the HPM room on the floor below right where it was because we could have the quantities we needed to feed up into the clean room. If we moved it up, we couldn't keep a proper quantity of HPMs up there. I think validation and repeatability, Jeff touched on a little earlier. You know, again, the whole being able to repeat what you're doing, and when you get into the life sciences arena, the validation aspect to prove it out time after time is critical, and that drives a lot of why we're doing these operations in the clean room.
And that's the measure of success of the facility. It's not to get it built and out of the ground, it's to get it validated so you can make product. The building is a means to an end.
Yep.
And the end is getting it validated and making stuff.
Saddlebag approach was one approach to maintenance and access. We're going to talk a little more of that later. And then protocol. And the triangle bubble diagram that Jeff had spoke to this somewhat. You can have the cleanest space, you can build the cleanest space. If you have terrible protocol and sloppy protocol as to how people gown up and don't gown up and go in and out of the spaces, you can lay waste to all of that hard work. It really is twofold. I mean, when you start constructing, say you start a new building, you're going to build a shell, and eventually you're going to get down to building a clean envelope of where the clean room is. From there, you're going to progress to activating air handlers with temporary filters, and then finally to a condition that simulates, you're done and you're ready to have the owner move in. You're going to start from a dirty environment, and you're going to progressively have cleaning protocol as a contractor to get to that end game. And then you pivot to operations, same thing. Gowning appropriately. I mean, full bunny suit is not comfortable. You got to have the temperature and humidity correct, but you only want to do the operations you absolutely have to in that suit. If you can do it in a dirtier clean room, a class 10,000 or 100,000, and you're only wearing a smock and shoe covers, great, you'd want to do that, and you can arrange your planning accordingly. The biggest contributor to contaminants in a clean room is people, whether it's skin cells or just any manner of fabrics or things that you bring into a clean environment. So can't stress enough that this operational element is also a key to success.
There are some similarities and differences between the clean rooms across the spectrum. We'll just touch on a few of them right now. One is materials of construction, and we'll have a couple of photographs afterwards to illustrate that. And the materials of construction are selected so that they're durable and cleanable. In the microelectronics arena, the cleanability is basically wipe down. In life science, it's wipe down and maybe something a little bit more. In high containment, you can fog the room with vapor phase hydrogen peroxide or chlorine dioxide, whereas in the electronics realm, that would be detrimental to the electronics, obviously. Air quality is key, and both from a positive and a negative pressurization standpoint. Particulate control, utilities in general, all these facilities will have water, deionized water, purified water, steam, clean steam, power, clean power, you name it, they'll have. And also pipe gases, which are kind of like unique to each one of those facilities. Some of the differences are, what's the overall focus of the facility? Is it to protect people, or is it to protect the electronics? If you're dealing with microorganisms or particulates. So are we protecting the people, the product, or both? And that's something that we do during the programming stage. Again, the certainty of outcome. How do you want this facility to operate, in its greatest sense? So again, if it's people or product, is it a barrier or a containment facility? And that has to do with the pressurizations. And on the right-hand side, a couple of diagrams that were extracted from a project. It was the Pharmaceutical project. So there are a couple of kinds of airlocks or anterooms. One's called a sink, where the air basically sinks into that room, so it's negatively pressured to the environment around it. And there were a bubble, where that anteroom is pressurized positively, pushing all the air out. So, or even even through. So in a sink situation, it's something that you're protecting product. In a bubble situation, it's something that you want to have the terminal room being the dirtiest. And in some cases, we have combination. Like, for instance, in this pharmaceutical project, which deals with flu vaccines, is not only sequential cleanliness level progression going into the clean manufacturing room, which is actually double negative, but also it's within a containment barrier, so it has to be negative to the outside. So we have a series of bubble and sink anterooms to achieve that pressurization.
Question real quick. Just going back to the validation process. Yep. Can you guys just talk about the validation process and, like, say you're aiming for an ISO 5, but you go to validate it and you hit an ISO 7? Does that ever happen? And if so, what do you do?
Not really. You hope not. Not generally. If anything, we're finding that the systems have enough in them to perform often at one level higher. You really don't want to cut it that close. I mean, you're going to use metrics, rules of thumb, past experiences. We've got some modeling tools we'll show you near the end. But you want to make good and certain that you have the ability to at least make the level that you're looking for. And again, often it can come to discussions about protocols. You might be well within the parameter to hit your target and above, and you find out that the user's not employing the best techniques for access in and out of the clean room. I've been into some clean rooms that the protocol is ridiculous, and you go in there and the clean room is awful. And then you have other ones where it's a beautiful clean room and they just, yeah, go ahead. they're not matching the level of access criteria and protocol to the space. So
The validation, is it a commissioning agent, third-party commissioning agent that comes in and says, hey, this certifies?
I'll let Jeff speak to that. It's really an extra layer. Commissioning is one thing to say we have what we have and it's working the way we want it to work. Validation, I think, speaks a little more on the life sciences side to the repeatability.
Repeatability of the
Documenting
process. There's commissioning, and then I think from a clean room particulate standpoint, certification.
Yep.
And then validation is actually you're validating the biopharma process. So the biopharmaceutical process has to be repeatable, documented to be repeatable. It has to have the same results, the same output. If you're passing steam through a system, it has to be at a certain pressure, certain temperature, and it's got to happen all the time. So that's, there's certain levels of validation, which is installation protocols, operation protocols, and performance protocols. So all those three steps lead to a validation program that will eventually, hopefully, be approved by the FDA so you can make product.
And trend data from the BMS and temperature and humidity tolerance bands and particulates, and continuing to, at periodic intervals, have the clean room certified and pass certification would go into that validation package. So they are linked. They are linked. But again, you never really want to be cutting it that close.
So, some photographs of some common spaces. On the left-hand side is a clean room. It could be an electronics clean room. It could be a pharmaceutical manufacturing facility. But a lot of the materials are the same. These are composite panels that are coated with polyvinyl chloride. The upper right-hand side is the walkable ceiling. That's right above that space. And then you could have a little bit of downgrade, some entrances to autoclaves. This is just behind the curtain. Again, some more examples of some of the products used in pharma. Resonance floorings, corner guards, crash rails, a lot of stainless steel. So,
kind of on a bigger scale, the air handling situation. On the left is the fan deck or upper level above the clean room at GE Healthcare outside of Albany, and each one of these is a central station recirc unit sitting on a curb, pulling air from below and pushing it back in. So all of that's happening underneath. There's a whole football field full of these things, pushing air down and providing the sensible cooling through a cooling coil to bring it back up. This guy here is a local bank of HEPA filtration where, kind of a similar but different manner, the air is pulled and pushed through a HEPA filter. Lots of airflow and filtration. As far as utilities, having an accessible path to distribute utilities and valves. Ask any facilities people, any facilities manager, they love valves. Being able to isolate one aspect of a facility or a branch or a tool or piece of equipment without shutting other things down, that's a good thing. And hazardous materials. Mentioned these some. Semiconductor process uses a ton of nasty stuff, toxic and corrosive gases. Flammable and pyrophoric, pyrophoric being it blows up when it hits the air. Generally good to keep in a cabinet that's exhausted and has a sprinkler head and has a nitrogen purge bottle in it and all of these other features. That's what you're looking at on the left here. Here's a mass of piping being distributed, distributing these different flavors of gases out to various pieces of process equipment. Smaller stuff you're looking at is type 316 orbitally welded stainless steel, 1/4 inch for the non-hazardous stuff. Larger stuff you're looking at, that's actually a pipe within a pipe. It's a 1/4 inch inside of a 1/2 inch. And the interstitial space is monitored for leaks. You can do it with vacuum or pressure. You're monitoring a change in that, which indicates that you have a breach in your carrier pipe. Again, you don't want that stuff getting out. Lots of hazardous production materials or HPMs to manage on these projects. Yes?
Question on the HPM regulations for storage and usage. Is that federally mandated, or can those regulations change depending on a municipality or a state? Or
it's really dictated by building codes. Building codes are going to dictate how many, the volume of HPMs that you can store in any control area in a building, any fire separated area within a building. As I mentioned before with the Cambridge example, as you go up in floors, it can reduce. It's more than volume too. Is it in use or is it stored? Are you piping and pumping out of this room if it was a flammable liquid chemical, for instance, or are you filling a tote and carting that tote down to its use point. That changes. How big are the containers? What's the material, the construction of the containers? How high are you storing them? Do you have containment? What kind of room do you have to storing them? So there's a ton of factors that go into how these are stored, and it's generally part of the codes. The building codes, NFPA, if you have an FM job, FM data sheets are going to come into play.
And then from the biomedical side, we have, horse of a different color, not so much chemical based, but also toxins and bacteria and viruses. And these are, there are guidelines out there, the BMBL, the NIH guidelines that assist in helping us develop environments for these. Yes?
I've heard stories in my discussions with people about how different companies, life sciences companies, are looking at spaces in downtown Boston buildings, and it's difficult to find a space that they can go into because of all these extra considerations. So can you talk a little bit about what are questions? Do owners actually know about these special considerations, design and construction?
Well, if they don't, they need to be educated. And and part of what we would do as architects and engineers is a due diligence. Take a look at the facility that they like to lease and basically give an opinion as to what it would take to bring it up to the regimen that they're looking for that specific agent or that specific process.
Every client's different too, and every client's at a different level of sophistication. We've got a few clients who, we're updating a system that they maintain that they know about. They know they can have X number of cubic feet of silane in their building and not a drop more. They can have X number of gallons of isopropyl alcohol in this part of the building and not a drop more. And the EH&S department will manage that. And when a researcher says, I need another 5 gallons of X, they say, no, you can have 2.5. And they'll be the gatekeeper for a lot of those things. But unfortunately, that's the exception and not the rule. And a lot of times you find that the way an outfit is operating their HPM inventory is not what it should be. So yeah, it falls on us to educate them as best we can, but we're not there during operations, unfortunately.
Yeah, and a big part of it is doing a risk assessment. I just finished a study for LabCorp down in Florida. They wanted to convert BSL-2 lab into 3 because they wanted to work on tuberculosis. And they said, well, what do I need to do? Well, to follow the letter of the law, you need to do X, Y, and Z. But if you're doing risk assessments and if it's just for diagnostics, you can actually back off your requirements. So basically, remember the triangle and the circles? It's kind of doing that analysis to see either from protocols, equipment, facilities, what you need to do to achieve your objective.
I'm moving on quickly here to energy. Somewhat generic graphic, but to explain it, about 40% it's going to vary. Let's say 40% of the energy consumed in a clean room is the actual equipment that the owner is using in the room itself. 10% is going to be process support utilities. Let's put lighting in there as well. Real message here is about half the energy going into the clean room is going to be for the environmental systems, the airside systems, and the mechanicals. Got it into 3 categories here: makeup, air, and preconditioning. And again, this is pointing back to some of the stuff we talked about before, but making people comfortable. And if you're in a gown, again, fully gowned up, you're going to be quite uncomfortable if it gets too warm. So creature comfort, the process requirements, what the space needs and the process needs, and what kind of tolerances. You can get into some very tight tolerance bands that need to be maintained in these spaces. Humidification is part of that, and the air you need for pressurization, and that again goes hand in hand with exhaust. How much are you putting into the space? How much are you pulling out of the space? The number and types of exhaust streams are going to be dictated by how hazardous whatever it is that you're pulling out. Generally, you're going to have a corrosive exhaust and then some solvent-based exhaust. You might need abatement and other environmental measures to contend with some of this stuff as well. And then the local reconditioning for sensible cooling. How are you continually removing heat from the space? So that's half of the energy in your clean room.
Question?
Sure.
So is there any case where the codes require or demand a local resource condition, just 100% on the outside here, such as BSL-4 labs or any other environment situation?
On the guess on the electronic side that I could speak to, the amount of makeup air coming into a space isn't going to be that much if you don't have any exhaust. You're just going to be accounting for leakage and positive pressurization of the space. Not that big of a deal. When you get into spaces that have a lot of process exhaust, you're faced with making up a lot of air that goes out the roof. There aren't that many regulations that I'm aware of. There's a new chapter, Part 16 of the ISO standard that just came out this year, but there isn't a prescriptive per se that I'm aware of for energy recovery, and we were just going to get into that a little bit because of some of the challenges we've had with energy recovery with these corrosive exhaust streams. As far as 100% outside air on the BSL-4,
It's pretty much 100% outside air.
yeah, yeah. But you, I mean, you were going to go here with energy recovery. You have more opportunities, I think, to do energy recovery in the life sciences at this point than we're seeing in the electronics marketplace.
There's to your point too, there's also a piece of equipment called a biological safety cabinet, and I don't know if anybody's heard of those. They're typically used in a BSL-2, BSL-3, even in BSL-4. But there are certain types. One is, a fully exhausted type, and one is that it recirculates into the room. And the A2, which recirculates into the room, exhausts about 30% of the air within the cabinet into the room. Okay, but that's already been HEPA filtered. But there's a kind of a cycle that goes within the biological safety cabinet of that remaining 70%, so it continually cleans the air, much like it would be in a clean room. So it's a mini clean room, pretty much. And the 100% exhausted air, the B2 biosafety cabinets, you have the room air coming in, going through a HEPA filter, going to the chamber, and then out the HEPA filter and 100% out. So you don't have that benefit. So a lot of clients will default to a type B2 hood because they think it's safer. But actually, in an A2, it's a little bit cleaner. So you have all these tools at your disposal.
I think the short answer to it is there aren't a lot of regulations, at least on the electronic side, that are hamstringing business. You've got to be safe. You've got to have a safe environment to work in, and energy is often the penalty. There are some things we're going to touch on here that try to move the needle a little bit with respect to energy.
Energy recovery, I think we all know about enthalpy wheels and heat recovery wheels and glycol loops and things like that. So those are things in the life sciences industry that are at our disposal. User education, just the simple thing of closing your fume hood sash and things like that, and occupancy sensors, proximity sensors for fume hoods. Those are the kinds of things that are available to help with energy recovery. Harvard University had this program of Close the Sash, and where they had the design teams basically have competitions, and each of the research teams would have their laboratories monitored, and at the end of the month, whoever had the lowest usage got a prize. Got a party, got a beer party. And then prudent planning. We talked about a box in the box. We talked about why do you do an entire class 1000 clean room when you only need a little bit of it? We'll get into something like that. And also, zoning the facility between lower levels of containment or lower levels of electronic particle containments and higher ones. So basically, you want to match the solution to the risk. So that's why risk assessments are so important, because you get to know at what point in time you have to have certain PPEs. You have to have certain cleanliness levels. And then there's a phenomenon now called risk-based ventilation that we can get into. So basically, when you do your risk assessment, you know how much air changes you need to provide, as opposed to a straight 12.
And the updates to the ISO standard defining clean spaces, and I'm going to point back to the chart I had early on that said prescriptively how many air changes an hour you ought to have for each clean space. We're moving away from that. We're in the stages now where we're moving away more from that prescriptive approach to an evidence-based or measured approach, more of a performance-based approach, and we're going to show you some tools that we've used to further that. But that's where there's a real lot of energy savings available out there, where you can even measure particles and throttle down airflow based on your particle count still looks good. So as for tools, data is huge in these projects, as you can imagine. Typically, it's in the form of there could be 50, 100, 200, 300 pieces of processing equipment in a clean room facility. And they all have varying requirements for cooling, for gases, liquids, drains, power. And managing that ever-changing data set is difficult. Parametric design is a tool that we've used for that. We're also going to touch on CFD modeling and then some adaptability tools. So data, to date, data has been kind of morphed to being part and parcel to a BIM model. Not always the easiest to access. Having data available outside of that model is a trend that's afoot at the time, at the moment. Go to the next one, Emily. Kind of the old way of doing business. It can range from painting paper dolls on foam core to trace paper to spreadsheets and then drawings, and there's ample opportunities to make mistakes. And data exists in a lot of different forms. And so here we are with parametric design. We've been using Dynamo as a platform for parametric design. This is a project we're working on where each one of these boxes is a much more complex piece of process equipment. You can see as an example. Take the worst case, length, height, width. You can assign other attributes, weight and all the utility requirements, name, make, model, anything you want. And you put it into the database that is linked through this third-party software to the Revit model. And then if you can switch to the next slide, really this linkage puts the data in one place that facilities and others can easily manage and manipulate. It could be Access, it could be Excel, it could take on a number of forms. Third-party linkage to the Revit model. You can go into the Revit model, you can stretch a piece of equipment from a 4-foot bench to a 6-foot bench, and the database changes. You can go into the database and change the length from 4 feet to 6 feet, boom, the model changes. So this is kind of a whole new frontier that we're looking into, and it keeps the data in one place and minimizes the opportunity for mishaps.
So take it one step further. Let's see, all these boxes are not pieces of equipment, but they're rooms. The rooms parametrically can be given square footages, volumes, cost per square foot, occupancy, hours per day, what the adjacencies are, the level of risk of the processes that are happening within those. And then from that, we can start to develop planning in real time, putting these blocks together so that if I wanted a BSL2, maybe that's the BSL3, what does that look like? How much envelope do I have? What's the efficiency? What's the cost per square foot? What's my operating cost on an annual basis? So we can learn how this building will perform, 5 years before it's built. And then go to the next one. And so and again, in real time, we could take those little blocks and we can say, all right, I want all my level 4 risks together. So that has an impact on the architecture and on the planning and on the engineering. So again, sitting with our clients, we can view these and start looking at all the permutations and combinations to get the parametric models and actually have the data extracted from these models in real time.
Computational fluid dynamic modeling has been something that we've been using more and more. It's an Autodesk-based package that we've been using. Very powerful tool, and we found a tremendous amount of applications in Cleanroom and monitoring airflow. You can get all kinds of graphical outputs based showing velocity of air, how long air is taking to get out of a space. Real quick example here, this is a bay from Bay and Chase Cleanroom. You can see that we've got a half dozen 4x4 fan filter unit, HEPA filters on the top of it, pushing air down. We cut a plane through this modeling at the user level. We've got 1, 2, 3, and a few more wet benches, big open benches in this room that are chewing up a bunch of wall space. And we were having problems with certification. The blue this is representing local mean age, how long the air is kicking around before it leaves the space through these sidewall returns. The blue was good. This was a little slower. We were having trouble with certification down here. If you go to the next slide, we did a number of iterations, came up with 1, 2, 3, 4 more 2x4 HEPAs pushing more air in selective places. We tried different places. We added more return chase, and we vastly improved this end of the clean room, and it passed certification. Very powerful tool, and this proved out basically that the tool works. How we got there? These are these wet benches, these big, massive, open areas. Original program for this project is that the chemical work that was going to take place inside these benches would be piped to central chemical waste collection tanks. That was value engineered out. as was the fact that into that scenario, the bottom piece of the bench did not exist, and the air could get under the bench and into the return grills. When the central systems get valued out, now we've got containers underneath each bench collecting the chemicals, and we've effectively blocked off the air path to the return chase. That's why we got into that modeling, and we snuck return chases into every corner we could find in the room, and we got it to pass certification. Just another example output project we're working on, and we sliced a section isometrically through this room, and what we were looking at is a 2-foot raised floor here. All of the air is coming out of the ceiling. The red is too high velocity, and what we're finding is that this perforated raised floor system, all of the air is racing that way and racing this way, and we're creating a dead zone in the middle. And what that led us to is finalizing plans for extra large openings in the perforations in the floor here, and then the outer thirds we're actually going to have floor tiles that have dampers in them, so we can throttle the airflow back and force the air more so to the middle. And we're finishing up some modeling on this. It's showing a much more laminar approach to air from the top down. But a very powerful tool, and we're getting a lot of mileage out of this on a lot of projects. You can figure it out before you build it, hopefully.
Some adaptability tools. These are items that are available in the marketplace right now, and they're continually evolving. But essentially, you can see what they are: some filtered fume hoods, which are independent of the main mechanical system, movable partitions, different utility distribution systems, movable casework. Back to your question earlier, in terms of taking an owner through a facility, these kinds of items will allow you to flex and morph the facility to match the evolution of their science, but the infrastructure that you install can be very, very minimal. So you're saving on first cost for the construction. You're buying these parts and pieces of equipment that get depreciated over 7 years as opposed to 25. So it's actually a good financial benefit in giving you flexibility and again, adaptability. Some of the trends we're seeing, here's a whole list of them. We'll get into them in a little bit more detail. But the one that's depicted over on the right-hand side is single-use disposable bioreactor liners. What this does is you basically run a batch. It's basically a batch kind of a system. And at the end of your run, you just take it out, dispose it, and it actually saves on clean in place, sterilize in place. So actually, you get a quicker turnover on your production. Next is some pre-assembled modules. What we've been seeing with a lot of our clients is that from a safety standpoint, from an efficiency standpoint, and from a quality control standpoint, they would like to have these central units. Then this is a photograph of a utility frame, utility bridge, that's chock full of ductwork and piping and conduit. They're either constructed in a factory or constructed on the ground, and then when they're all complete, they're just lifted into place. So you really limit the amount of overhead work that you're doing. And basically it becomes standardized, and it's tried and tested, and you're actually working at off the ground as opposed to ladders and platforms. And then again, there's some modularity above and below the ceiling. On the left-hand side, that's a powered data pole that has been used in certain locations. It runs on casters. It can be moved anywhere on the dance floor, plugged in where it needs to plug in an overhead service carrier. And actually, the actual workstations are dumb. They're not electrified. All the utilities are distributed through either a hitch and post or ceiling or something like that. Prevention through design. This is promulgated by the National Institutes of Occupational Safety and Health. And basically, it's a program to initiate design early on, initiate safety early on in the design process. We don't want to rely on the contractor to be the safeguard, the vanguard of safety. We need to start it earlier on. So the program is designed to eliminate hazards, controlling risks, optimize processes, and enhancing the work environment. So safety is not only during construction, it's during operations as well. And so basically what we're doing is moving safety upstream in the design process where it's cheaper. And the certainty of outcome is such that it results in lower accident rates, because a lot of things are done modularly within ergonomic range. And then the within the workplace itself, it's a safer environment. Mini environments, Brad had mentioned before, in some instances like in food and beverage, the Nestle bottling line, where there's only one section of the line that really needs to have an aseptic situation, and that's what we're seeing more and more, especially in microfab and also in biotechnology, where the critical processes need to be in a higher cleanliness level. They're actually enclosed in a more robust enclosure.
A few other trends, and these are picking up on some of the things we've said already. Left picture is kind of a more traditional setup you'd see for utility distribution in a clean space, where it's fixed, it's constructed, you want to change your equipment layout. You're forced with repiping and revising that set of stanchions with the air, vacuum, and nitrogen lines and whatever else you might have power on there. The right approach mimics a lot of the things that Jeff had pointed out earlier. This is actually a project that we recently completed with Chapman, and we've got these mobile benches. They have actually a cable and tube management system on the top of them. We get more and more clients who are looking to do a uniform grid of utilities, the basic utilities. You add the specialized ones where you need them, but the basic utilities, air, nitrogen, vacuum, data, power, grounding strip, you put all of that in every panel so that you can have this equipment layout today, you can have a different layout tomorrow, you can swag your utilities onto the hooks and poles and have your work surfaces, and you're not constructing and deconstructing every time you want to change things up. You saw this picture earlier, but the story behind this is GE Healthcare, and this was a time saver and a cost saver in that rather than a full subfab, full basement access, to access the area above, the clean room above, we used modular precast concrete tunnel sections and created an alleyway down underneath the clean room and racked all of our process utilities on either side. You can see some cross members, and then stood up off those cross members. What you don't see is traveling quite a distance left and right is the actual ballroom, clean room upstairs. So the utilities are rising up off these racks, offsetting onto the floor. Is an example of, you've got a perforated raised floor, and periodically you have these vision panels where you've got access to valves, gauges, and again, the isolation valves for branches and different pieces of equipment. So you got good access. This is a trend that isn't going away with the underfloor distribution. And lastly, one of the last things we have here is, I mentioned space application, defense, things tied to government contracts. SCIFs have been around for a while, and many of you I'm sure have heard of them, but a secure compartmented information facility, where secure communication, secure activities, meetings, events take place behind closed doors. Some of the features of those, what we're seeing is a blending of those in clean rooms. So some of the features of a standard SCIF are, you've got an STC rated envelope. You generally got multiple layers of drywall, often a layer of RF shielding between the layers. You've got any ductwork passing through the space, 96 square inches or larger. You've got man bars in them with an inspection port, white noise generators in ductwork and chases. You've got surface mount electrical. You don't want to mess with the integrity of the secure envelope you're creating, so everything's surface mount. In addition to general data coming into the room, you often have a local server, cable tray under the ceiling, and you're running a classified local network as well. Any piping coming in and out of the space is either grounded or it has a section of non-metallic piping built into that. Now, try to do that in a clean environment. You're in a class 100,000, not so clean space, not so hard. Try to do it in a class 10, class 100 space, class 1000 space. You don't want to run a cable tray under a ceiling. Maybe you want walkable chases inboard of the secure perimeter to run your classified data in. Whole host of challenges, but more and more companies are finding themselves not just building SCIFs, but building SCIFs that are also clean rooms. A couple quick images. On the left is the first layer of drywall with the RF shielding on top of it. You can see how it's overlapped down onto the floor. It's woven in around the open web joists and to the deck above. And then the final face of drywall will be put on the inside of that. And phone kiosks. You walk into a room like this, you don't bring your electronics with you. You put them outside, and if the client's nice, they'll even give you a place to charge your phone while it's sitting there. And this is the last topic, is just giving a nod to some of the new materials. On the electronic side of the house, upper right-hand corner, there's your wafer with all the computer chips built onto the wafer, silicon substrate, and It's been used forever, and other materials have as well, but we're seeing a rise in popularity in some alternate materials. Gallium arsenide is one of them, a different substrate. It's got better mechanical properties for harsh environments, like what if your chip is going to be on a satellite and be in space? It's going to be extremely cold, extremely hot. They perform a little better. But the flip side of that is now you've got all kinds of arsenic wastes in the airstream, in the water stream. So you've got a whole additional layer of costs associated with collecting and treating those hazards.
There's also a convergence between microfabrication and life sciences. In the lower right-hand photo image, it's a nanotube and made out of carbon. And the nanotubes are a conveyance for small molecules to deliver drugs. And these can be targeted within the bloodstream and brought to a specific site. MEMS, microelectromechanical systems, are also on the rise. Again, these are extremely small. Years ago, the U.S. Army had done some study with MEMS to, again, as little robots to deliver drugs into the body.
Picture each one of these computer chips, traditionally stationary circuitry, and some of them now you've got gears and moving parts in them. Pretty crazy stuff at a tiny level.
Yeah, so essentially, and that's going to wrap things up for us. We're looking at, in terms of the design of these clean spaces, looking at the parameters at which you want to design to. What are the codes, what are the regulations, and how can you use those to formulate your designs in a beneficial way? Looking at safety, looking at cost of ownership, and looking for a certainty of outcome.
And looking and leveraging the tools that are becoming available, and more stuff's becoming available every day. Parametric design, CFD modeling, there's great tools out there if you know how to use them. Thank you.
Thanks.
So much, that was very informative, and I hope you all took copious notes, but the video will be on our YouTube channel. Were there any additional questions at this time? I know we're a little bit over time. So quick scan of the room.
I just had a quick question. If you're doing an estimate for a client, do you have any sort of like a square footage number that you could put to this for a certain, or an ISO 7 or something like that?
I want to buy a car, how much is it? I mean, it depends on what you want to do, what the levels are. I mean, starting with pure electronics laboratories, data laboratories, computational based. You can, I really don't want to put out a number. Chapman, I'm sure, can give you a number on that. But as you progress higher and higher, biological laboratories, chemistry laboratories, the more intensified laboratories, up through biosafety, levels that can be $1,500 a square foot. So it's going to depend on fume hood intensity, air exchange rates, your risks, the materials. Yeah, I'm sorry to be so glib about it, but that's it's kind of an open-ended question.
Getting back to the point Brad made about energy, right? Microelectronics is going to be well over 2,000 square foot because of everything that's going into it and is being consumed.
Well, I forgot it's in Boston.
One other question.
Thank you both, Jim. You talked about the pressurization or depressurization of spaces, and what is the standard applied for the porosity of the assembly and closing that space?
Depends, like everything. You're going to have rules of thumb that you're going to apply to. Generally, you're going to have a fairly tight envelope. You're going to have a fairly tight envelope. Your outside of your chase walls are going to go and they're going to be sealed to deck or to some sort of plenum, and then you're going to have your inside clean space and then chases for the air to go, all within this contained box. They generally want to be tight. When you're planning makeup air, you might plan somewhere in the order of 100 CFM per opening. So you've got 4 doors in and out of the space. So you need 400 CFM to account for leakage, and then you need a couple other 100 CFM to make sure you're positively pressurized. 600 CFM. Then you've got 400 CFM of exhaust. Well, now I need 1,000 CFM to accommodate the makeup for the exhaust. But you're accounting again. 50, 100, 200 CFM per event in the perimeter walls of the opening to account for leakage. But it depends also on what you're doing in the space. Like we do rooms that are dry rooms for lithium-ion battery manufacturing, and they are extremely dry. And as you can imagine, the moisture just wants to get inside. So we build them out of insulated metal panel, freezer panel construction, and you're sealing and gasketing and caulking everything. So you're really bringing that porosity and that leakage down to almost nothing. You still have to provide some for pressurization and exhaust makeup, but depends on what you're doing as to how critical it is. If you have a class 100,000 space and it's not all that tight, it doesn't really matter, other than the energy you're going to spend on the preconditioned air.
From a containment standpoint, the biological containment, if you're doing a BSL-3 facility, for instance, you would normally, perhaps the lowest grade would be an epoxy paint over drywall, and that would be the level of integration. Containment in BSL-3 is done via directional airflow. All air is going into the space and not escaping. So if you have little fissures, it's okay. You have little leaks, and you want like a leak under the door in order to maintain that containment. A BSL-4, for instance, basically the primary containment is the room itself. So that goes through what they call a pressure decay test. So that room has to hold 2 inches of water for 20 minutes and not drop. So you can see that that's got to be basically a lined pool, if you will. And those will have polymetric coatings anywhere from 60 to 90 mils. I mean, thick.
Thank you. So Jeff and Brad will stick around for a little bit,
Sure,
right?
yeah.
Answer any more questions. Please, thank you again for coming, and please stick around, have some conversation, enjoy some food and beverages, which are in the room over here. I'll open that door, and also one in the back. So thank you. Enjoy.